I hate you. You have a boomer that's drunk. You don't have it before. Hey, I'm dangerous. Let's just get it comfortable. Yeah, I mean, I think you're like, even if I was, I'm going to be allowed to one.
Hello? Can you hear me? Very proper. Also one, year one, year one, the young, today we're going to talk about array antennas, Fresnel zones, and relay distance. So you're going to see how we can make more sophisticated antenna by using multiple elements and have them work together. And what we have learned previously is just Hertzian dipole, which is very simple. Mathematics of it is also very simple. It has a radiation pattern that looks somewhat like this. And it has a rather poor directivity. Directivity is a measure of how directed the energies are. And apparently the directivity is not very good because the radiation pattern is almost isotropic in this direction. The only direction it doesn't radiate is in a null direction along the axis of the dipole. You can say that your monopole antenna on your Wi-Fi base station, for instance, is a Hertzian dipole because the wavelength is quite long. When something is small compared to wavelength, it acts like a Hertzian dipole. Or your antenna tower that you have for AM920, which is a very tall tower. You can also think of that as very much like a Hertzian dipole because that antenna tower is so small compared to wavelength. Because AM920 has a wavelength of about 100 meters, I believe. So you can have high directivity antennas by having many of them working together. And if you have many of them working together, they can interfere constructively and destructively with respect to each other and direct the energy in a certain desired direction. You can also have automated radar. For instance, most cars have that now. both in the front and the back, so that we can avoid collision with other kinds of vehicles around us. So we're going to look at antenna array, which is chapter 30 of lecture note. We're also going to look into Fresnel zone and Rayleigh distance. Okay. So we derive a far field radiated by an array of dipole antennas. That means that just instead of just one dipole, we put an array of them together and see what happens. And that can enhance the directivity. And we can have broadside as well as end fire. I think this term comes from the sailors. Okay, when they put all the cannons on the broadside of the ship, they fire in the broadside direction, and when they put the cannons firing in the forward direction of the ship, it's called the end fire direction, or maybe in the rear direction of the ship. Okay, so antenna terminology also adapted these two terms. And when the approximation is valid, and when is it valid? That's the most important thing. And we look at the Néel zone, Fresnel zone, and the Parr zone, and look at the behavior in each of these zones. So let's look at the integrals that we have in the radiation integral that we have in the field. We say that as long as we have an ability to calculate vector potential, and we say that this vector potential can be calculated in closed form if you know what the current is. It will be the convolution of the Green function with the current. The Green function can be written in this manner. Okay, so this is the Green's function. And this, of course, is a current. And once given the current, in order to find the vector potential, we just need to convolve the current with the Green's function. Of course, this is easily said and done. When I ask you to do the convolution, you probably will have to pull your hair out because these integrals are not easy to perform, except for a very simple case. When we have the current to be a Hudson dipole, then we say that the current can be written as the current moment times a delta function, where this is the shorthand notation for delta x, delta y, delta z. Okay. But other than that, you can't do very much when you have this very complicated integral. So we seek to find a way to approximate this integral. And the way to approximate this integral is to notice that r minus r prime can be approximated as, I think many of us have actually studied this. Say if you have two vector r and r prime, if you take the difference and find the magnitude, this will be the difference. And then you can show that the difference can be written by the magnitude of the original vector r minus r hat dot r prime. Okay, that is what you can find. This can be proved by many ways. One way is to use the parallax method by symmetrical argument. Let's assume that this point is taken to be very, very far away, way outside the range of this taper. Then if you were to draw the r minus r prime, it is almost going to be parallel to r. The two vectors are going to be almost parallel to r. Then if these two are parallel to each other, then the difference in the length is just equal to that. And what is that distance? That distance is just r prime, the position of the source point. R prime is a source point. So every R prime that we have in here can be taken to be a source point. And you notice that this distance, R minus R prime, is just this whole distance R minus this little distance here. So you can prove this by geometrical argument very easily. You can also prove it algebraically. The algebraic proof I show in the lecture notes, okay? But let's take this to be correct. Then what it says is that this integral can now be approximated as if I put this in here, then this term is independent of R prime. So I can actually write this as R, taking the fact that the magnitude of R is R itself. Define that to be the way. And then if I make that approximation here, I can take the term that is independent of R prime. R prime is the integral variable. I can take it outside. So I can take one of the two terms in the exponent outside. Moreover, the denominator, I'm going to make a good approximation and say that this is just equal to that, and it's going to be just further approximated as 1 over R. Okay, so I don't take great care in approximating the denominator for good reason, but I take great care in approximating this term and exponent as two terms. The reason being that if you make R and R prime to be, or R to be much, much larger than R prime, this actually is a very good approximation. This is actually a very good approximation of the denominator. So I can take the whole denominator and put it outside. And what I'm left behind then is just to have an integral. I should say this is volume integral. Okay, JR prime. And then I keep this term inside. This becomes a plus sign now. Okay, can you see this approximation? I keep everything that is not associated with R prime outside the integral, and I keep only the term that has R prime dependence inside the integral. And if I look at this exponent more carefully, I can define it to be looking like this, where I define my beta vector to be just beta R hat. So you can see that this thing can be written as such. What rings a bell when you look at a term that looks like e to the j beta dot R prime? What comes to your mind? What can, yes?
The solution of the wave.
Right, it's a solution of the wave equation. It is a plane wave, right? Except that this plane wave is propagating in the opposite direction. Okay, so if you look at this integral more carefully, if this is something like this, it is also so it is also expressible as just a integral over the volume j of R prime e to the minus or plus j beta dot R prime. And what comes to your mind immediately when you stare at this integral? Does it ring a bell, or does it conjure up an image as to what integral it is? Yes, Logan? It's the Fourier transform integral, right? Because I can choose to explicitly write this exponent as in its explicit way. It actually is a 3D Fourier transform. But there's one big difference about this 3D Fourier transform. Does anybody know what the big difference is? This one, is right. I guess in electrical engineering, when you think Fourier transform, you always think about Fourier transform in time and space. Okay, but to a mathematician, he or she may not think that way. So, but there's something peculiar about this Fourier transform. Yes?
It has to satisfy the square relation.
Very good. Okay, very good. Very good. Yeah. Zulo, right? Joseph Zulo. Very good. So this is a usual kind of Fourier transform in the sense that this has to be true. This has to be true, meaning that it is a Fourier transform with a beta vector fixed to a length. And that fixed length defines a circle in the Fourier space. Whereas ordinarily, if you have a Fourier transform, there's no such a fixation on the amplitude of this thing. Okay, so this defines a circle, and that circle is what we call Ewart sphere in the Fourier space. So it does define a Fourier transform, but it does not give you Fourier data all over the Fourier space. It gives you Fourier data only on a sphere. And that sphere is called the Ewart sphere. And some physicists will call it the energy sphere. Okay, but they all mean the same thing. So now we can use this approximation to study radiation from an array of dipoles. And actually, you can develop quite a bit of physical intuition. Because as an electrical engineer, you know a lot of things about Fourier transform. Especially if you have studied a course in signal processing. You can juggle Fourier transform properties back and forth in your mind. So let's look at a very simple case where we have an array of dipoles. And we say that these dipoles are all pointing in a z direction, but they're all located at different places. Let's assume that the first one is located at x minus d0. So I define the location as such, and then the next one is having a different amplitude, but located at x minus d1, and so on. I can write all of them down, but it will be very tiring for me to do so. So the last one might be located at x minus dn minus 1. Okay, and close the bracket. And then I have to multiply by the fact that these are point sources in dipoles. So I have to multiply by delta x and delta y. So I have defined this current distribution as a linear superposition of radiation by an array of Hertzian dipoles. Now, the next thing I do is the mathematics. Okay, I substitute this thing into the previous integral that we have derived, and then the previous one that we have derived even, to find our vector potential A. And we are ready to do that. And if you now look for your vector potential A, we were all pointing in the z direction, so I know that this is this common factor. And then there's a spherical wave out front, because when we make the approximation, we say that there is actually a spherical wave out front. Okay, you put that out front, and then the rest is just integration. So if you evaluate this thing now, you will have a volume integral dr prime A0 delta x minus d0 plus A1 delta x minus d1 plus blah blah blah, and you know what I mean. Okay, and then you have to again multiply by delta x prime and delta y prime. This should be prime. Okay, this should be prime coordinates since they represent the source location. Okay, and of course, this integral is not complete unless you put in this phase factor. This phase factor is very important. Okay, we have to put in that phase factor. Each of the dipoles would have a different phase, is what the phase factor says. And then if you work out this beta dot r, it's actually beta r hat, so it should be r prime, okay? So r prime. And if you work this out carefully, and let's assume that this problem is 2D, and that we are only putting the observation point in XY plane to make life simpler. Okay, I can of course observe in the 3D space, but that would mean that you have to do more mental gymnastics. And to make life simpler, let's assume that you're observing the field in the XY plane. So the beta that you have is always pointing in the XY direction. Remember, r hat is the direction of the beta vector. So your r hat is going to be in this XY plane as well. And if you work this out, then it will be beta x hat cos c plus y hat sine c. This would be my r hat. Okay, dotted with r prime, which is x prime plus y prime. Okay, you can work that out, and that is quite simple. And then you would take the dot product. Of course, the top dot product will come out correct. And then what you have then is that you have also the shifting property of the delta function. So your x value needs to be only evaluated at this value. So the x prime value, this would be, sorry, x prime, and x prime here. The x prime here as well. Okay. So finally, the integral that you have, okay, will look something like this. With a spherical wave out front. And then each of these terms can be evaluated in closed form, be something like A0 e to the j beta B0 cosine C. Those are the cosine C coming from here. Plus A1 e to the j beta D1 cosine C plus the last term, which is an minus 1 e to the j beta Bn minus 1 cosine C. Okay, can you see the trend? Okay, so this is still rather complicated. And this is a complicated sum, but we want to make life simpler. And let's make the life simpler by choosing a form where you can sum this series in closed form. Okay. So let's choose the form that Bn is NB. And we choose this to be the case, then all the array dipoles, the dipoles are equally spaced. Can you see that? All the B's of n are equal the n times d, which means that they're all equally spaced. And if you do that, then we just have a linear spaced array of dipoles, where the spacing between them is d. Okay, then the A that we have would be ZIL, mu IL, over 4 pi r e to the minus j beta r. And then because we pick n equal to 0, the first term would just be 1, and then the second term will be e to the j beta d cosine phi. Okay, and let's assume that A is having an amplitude of 1, but a phase factor. Let's call it phase factor AMC. Okay, so if you were to do that, then if you were to plug in and put in the proper thing, then the second term should be something like this, plus JC. And then the third term should be something like plus e to the J2 beta D cosine C plus J2 C. And then we can go on and go to the last term. And the last term should be something like e to the j n minus 1 beta d cosine c plus phi, something like this. Okay, that was the last one. So what you notice is that this sum can be summed in closed form because it is of the form of 1 plus x squared plus x cubed plus x to the n minus 1. If you look at this sum, okay, all of us know how to sum this series in high school. Okay, we know how to sum this series in high school because we learned that when you have x to the n is equal to 0 to n minus 1, it will be 1 minus x to the power n over 1 minus x. Okay, so if you do this, then you can sum this in closed form. It will be something like this, and then we just identify x to be e to the j beta d cosine phi plus j psi. And then you will find that this thing will sum to something like a of r is approximately equal to c hat mu il over 4 pi r e to the minus j beta r. And then the summation, which becomes just something like this, e to the j n beta d plus beta d cosine c plus psi over 1 minus e to the j beta d cosine c plus psi. Okay, so can everybody follow the mathematics? Quite easy to follow because we have some approximation of before. And for this equally spaced array with linear phase, the phase is increasingly linear. So not the dipole array. The vector potential can be evaluated in closed form in terms of this. Okay. So if you were to find the radiation pattern, the radiation pattern can be found from the far field. And we know one thing that you know that E is J omega A minus gradient of T. That is something that we learned very early in the course. But when we take this to the far field, what two components are left with this electric field? If anybody knows that, if we take this expression for the electric field in the far field, what becomes of it? Electric field becomes, the field becomes a spherical wave out there. Okay? A spherical wave is going to look like a plane wave. Okay? So if this is going to have the character of a plane wave, electric field will have these two components left. What are the two components out there? Okay, say this spherical wave is the propagating the R direction. And the electric field has to be orthogonal to the R direction. So in the spherical coordinate, we have only two components left. What are the two components? Very good. Okay, it's going to have phi and theta left. So it turns out that the wonder of mathematics will show you that there are components that cancel each other. And you can only have this left. Okay, I'm not going to show you the mathematics, but from the physics, you can see that this has to be the case. The electric field, the vector potential has to transfer. The electric field has to be transferred to the direction of propagation. And hence the electric field has to have only theta and phi left. You only need to worry about the theta and the phi component of this vector potential. The radial component, don't worry about it. That's what the story is telling you. So if you have the electric field in the far field, it's going to be proportional to A theta, theta hat, plus A phi hat. Then the radiation pattern, which is the plot of the electric field, okay, is going to be proportional to omega A theta. I guess maybe I can just write this for simplicity. You figure out what is it. Okay, that is the field pattern is going to be just that. And if you confine yourself to be on the XY plane, if you confine yourself to be on the XY plane, and you can imagine yourself to be on the XY plane, the electric field will only have one theta component. No more phi component. Okay, so I can actually throw one of the terms out and say that if I confine myself to the XY plane, this is just going to be just that. Can you see that? So if you imagine yourself in the field, the electric field has to be transferred to the direction of propagation. Okay, you only have the theta. Because another way to see it is that the electric field is proportional to G hat. The vector potential is going to be proportional to G hat. Z hat is only going to have a theta component, not a phi component. So actually, when we get to this stage, the G hat component is already zero. Okay. So another way to say that is that Z hat only contributes to this. Just A is Z hat something something. Okay. So you can work this out. You go back to your previous expression here. Take the theta component of this. That's quite easy to do. if you have a unit vector v hat, you work that out. And then you will find that there is a, I guess, there is a sine theta in that, but we are on the x-y plane. So that sine theta is 1. We are putting ourselves on the x-y plane to make things simpler. Okay. So finally, you find that this thing is the amplitude of the electric field times this very complicated thing. This is rather complicated looking, kind of daunting, but we have no fear as electrical engineers as to how we should simplify it. What you do is that you pick half the exponent outside. Half the exponent outside is non-constant. And then you pick magnitude of those half exponents. The sine and the cosine. Do you see what I mean? So I can take half exponents outside. And then what I have left is half exponents inside. Minus e to the plus j half exponents for the second term. I do likewise for the denominator. Half exponent inside, and then half exponent okay. Then I will have a half exponent out here. Can you see this kind of mathematical trick? We all going to do the process. So if you were to take the magnitude of this, it was the magnitude of this times magnitude of this. This complex variable, magnitude of product. And then you see that the magnitude of this is 1, but in a difference of two exponential functions, what will it become? Yeah, the actually will become 5 because we have a minus sign. Okay. So if you do this carefully, you get something that looks like. Let me simplify things and say that this whole thing is going to be proportional to sine of n x over sine of x, and you can figure out what the x is. It's just something that you have to plug in. Sine of n x is a sine of x. If you're a sigma processor, what do you call that? Now you're a sigma processor. The circuit designer. No. Okay, anybody know the name for this thing? Okay. There's a precursor to this. I think every one of us knows this function. The thing function. The sigma processor always have to live with what? It's not a digital thing. Okay. I'm not a sigma processor. It's called a digital thing. Okay. It's not a digital thing. You have it in terms of the digital thing. And then you can just plot the radiation pattern as a result. Okay. And there are two examples given in the lecture notes. You can pick the phases between the array elements. You can also pick the numbers of array elements. And here's an example where you have the spacing is such that beta d is to the pi, the phase is 0, and then n is equal to 5. Okay, and you can plot beta is equal to 2 pi over lambda, and then you can take d equal to lambda over 2, halfway point. Okay, and this is the pattern that you arrive at if you look at the design. So there are certain things that come to your mind when you look at this statement. This is 0, that means all these 5 elements are equal. Okay. And they will interfere with each other constructively and destructively. They interfere with each other constructively in the y direction and the next y direction. That is called the dot side. They interfere less constructively in the empire direction. And if you had only 2 of them instead of 5, and one is 180 degrees out of phase with respect to the other one is what we say. Beta d lambda over 2. Okay? So if you look at the phase difference between the framework that comes out in the horizontal direction, the 180 degrees out of phase. That means that the tensor is side in the horizontal direction. But then we don't see a complete transformation in the horizontal direction. Why is that so? Yes. I think you can have 4 elements who will cancel each other's perspective. And we have nothing happening horizontal. But we don't have perfect cancellation in the horizontal direction. What is the reason? We're just going to do sanity check on our solution to see the solution of the problem. What is the sanity check that tells you that this pattern is okay, not insane? So I have 2 elements that will cancel each other. What happens to the 2? They will not cancel each other, right? So this is 5 elements. There's no perfect horizontal direction. The one is here have a small, and then the other is just to constructive and destructive interference. And this is the other one. Okay, we make beta d thicker. Oh no, sorry, it's the same. We make the space pi and pick 4 of them. Okay. And when you have 4 of them, they are not completely out of phase. Okay, 1, 2, 3, 4, and you get a maximum in this direction. However, you get destructive cancellation in this other direction because the elements are actually out of phase with respect to each other. So if this is 180 degrees out of phase with respect to each other, this is 180 degrees out of phase with respect to each other, they cancel each other in this direction. And then they add constructively in the horizontal direction. This may not add constructively with this, but this one will add constructively with this. And this one will add constructively with this, and you have a gain in the power in the horizontal direction. Okay. So you can do some sanity checks if you need the plot. Any questions regarding this design of an planar array using a number of elements? And as you can see, the magical thing is that you can get this pattern to be horizontal or vertical, broadside or end fire. The magic is that you change the phase. You change the phase. And this is wonderful for us because if you're an aesthetic controller, you want the phase array to track the action. And you see that some old technology still uses the gradient, but in principle, you can use electronic phase. It change the direction of the antenna array to practice as plot. Okay, maybe there's still some reason why they still use that rotating one. So now, but you can see that in S4, you still have antenna that rotate for some reason. Logan, you know the reason?
Oh, no, right. There, you see by changing the phase, you get a symmetry. Maybe calling them to the typical. So by changing those phases, the phase intermediately, you get this rotate these radiation patterns to the phase of force. So you can have this kind of phase system that's a very important technology. You have to connect the everyone eventually a good phase. Yeah, if it's high over 2, it will be directed.
So you can play around with this, and maybe you can even write the MATLAB program to see how the pattern changes. So we did make far-field approximation. We say that R minus R prime can be approximated as R minus R hat dot R prime. So when is it valid? We put this in the exponent. And say that this exponential thing can be written as such. And we are not too careful about the denominator. We say that the denominator, we're just going to approximate as such. Why is it that we're not too careful about the denominator, but we have to take great care to make this approximation? Does anybody know? Yeah. Okay, very good. Okay. This is going to be a slowly varying function of phase when you're in the far field. This very strange thing happening to me again. And I don't know why all these things become very small on the left hand side. Somebody has a way to repair this, right? Why don't I just is there a reset view?
Yeah.
Okay, wonderful. Okay, thank you. So, but as Lackney said, this is a slowly varying function, so we just replace it with 1 over R, it doesn't matter. But beta times this has to be done with caution when you approximate this, because beta can be a large number, or beta R can be a large number, okay? The frequency can be high. So beta is omega over C, which is 2 pi over lambda. So if this R prime compared to the wavelength is not small, there could be a phase shift that is important up here in the exponent. Okay. So you better be careful and keep this from there unless you're convinced that you can ignore it. Okay. So the moral of the lesson is keep this term up there for accuracy. Okay. So you can actually also prove this algebraically, because I can write this as r minus r prime dot r minus r prime, and then I can go through all the kind of things, and it's quite a bit of algebra. It's how to prove this algebra. So I like to read the lecture and show that it's just high school algebra. You can follow the algebra quite well, and you'll find that if you keep everything in place and ask yourself when this is approximately correct, you find that this thing can be written as a power series. What we have done is actually just the first term. If you keep the second term in a binomial expansion or Taylor expansion, the second term will look something like this. And if you keep the other term, you'll find that the other term will look something like this. Okay, so we assume that r prime is small. In mathematical parlance, we say that this is order 1 in r prime. This is order 2 in r prime, because it's r prime squared. So is this term proportional to r prime squared. Okay. So these two terms are of higher order if we speak the language of a mathematician. Whereas this is the first order term, this is second order term. So the question to ask is, when can we pull out the second order term? If you plug this into the exponent, it's not that obvious that you can pull them out, because they will contribute to a small shift as well. Okay, so if you read this carefully, you find that the criterion for pulling out the second order term is r prime squared over r, much less than 1. Okay, so this is not obvious when you just did the first term. You don't know when giving the first two terms is good enough, and that is the criteria. The criteria for you to draw the third and the fourth term. That has to be the criterion, and if that is true, you plug it back into the exponent, then the approximation is good. Okay. So this gives you a certain notion of sizes. So if you have an antenna, your r prime is your source location, your r is the observation point. R prime might be there. And it says that the ratio of the source point to wavelength compared to the distance to the observation point, this ratio has to be much less than 1. It says that if the frequency is very high, theta is 2 pi over lambda. So if theta is very large or lambda very small, this criterion is harder to satisfy. Agree? It's harder to satisfy this criterion for short wavelength. So if you have a group of forces, if you want to be in the far field of this forces, you have to look further away when the wavelength becomes shorter. Does this make sense? So if the wavelength becomes shorter, you have to go further away. Another way of saying is that if this size of this antenna array, okay, is large compared to wavelength, the yardstick in electromagnetic is always wavelength. How many times wavelength is this array? And if it's too large, you have to go even further away to make the partial approximation. So there are zones that are not quite in the far field. Far field, you know how to get there. You just make sure that this criterion is satisfied. Then you are in the far field. But there are fields which are not quite in the far field, but the Fresnel zone is pretty obvious and frequently used in optics. Okay, that is not quite the far field yet, but you can see real power flowing in this radiative zone. And if you're in the near field, you can see that most of the power is reactive. Okay, this is the near field, the reactive zone, the Fresnel zone, where you start to see radiation energy. And then the far field things truly radiate. And if you look at the Poynting vector over here, it's fairly real. Okay. So this is just a Gaussian beam. Gaussian beam is quite popular. And you can actually find out the distance in which the far field will be important. It turns out that the distance between these different zones are given by, say, 2d square over lambda. Okay, and there's this zone here. This will be d square over lambda, and this is 0.62 d square over lambda, and those are the zones. And you can see that this demarcation point actually comes from this formula over here. Just we have this formula. R prime sort of denote the size of the aperture, or the d. Okay, and beta is 2 pi over lambda. If you put this thing into the formulas and work out the demarcation zone, and you find that these demarcation zones are reflected or indicated by d square over lambda, where d is the size of the antenna, and it could be your laser pointer. Okay, the size of the laser pointer. How big is that? Compared to lambda. Of course, for laser beam, the lambda is very, very small. So you have to go quite far before you start going of the laser pointer. Most of the time, you're not in the far field of the people. Maybe for now, don't want to do the function. But for long wavelengths, it's quite easy to go to the far zone. For short wavelengths, it takes quite a bit of walking before the far zone. Because the laser beam can remain polymetric. It doesn't look like a spherical wave at all. Here is just a picture of a Gaussian beam, okay? And we'll talk more about Gaussian beam later on. And this distance is called a Rayleigh distance. So Rayleigh distance is the demarcation distance where you can go from the Fresnel zone to the far zone. Are there any questions on that? The next topic I'd like to talk about is actually the next chapter on different types of antennas. I thought this would be important because antennas can be very easily made, but they cannot be analyzed very easily using closed form solutions. You usually have to use a numerical code to analyze antennas of complex structures. So we are going to motivate ourselves with heuristics. Okay. And we are going to motivate ourselves with physical insight in studying this kind of antenna. There are no more closed form solutions for us to play with, like if you do a Hudson dipole, you have the closed form solution. You have an array of Hudson dipoles, you also have a closed form solution. But unfortunately, in this world, closed form solutions are hard to come by. So we have to rely on approximate solutions. For numerical solutions. So computers are very powerful now. If you give Maxwell's equations to a computational scientist, you can solve the equations for you, and that field is called computational electromagnetic. Okay, so given any Maxwell's equation, you write them as such, and then you can Faraday's law. And then you have the other two Maxwell's equations which follow from the first two. And you can give them a very complicated geometry, and you have a source radiating in this complicated geometry. The computational scientists can figure out the solution for you by using a computer program. Okay. So many commercial software are available now. There's some from ANSYS, PSP, Dipole, some that I can name, and then NSOF used to be put out by an electrical engineering professor, but it got bought by ANSYS. And then a big industry that does this is electronic design and automation. And the companies that do EDA are people like Symmetrical, Siemens. I think this is still one. Okay, then. Okay, of course, Intel and the other companies also do a lot of this simulation stuff. And also, solving Maxwell's equation numerically is important in ICD or integrated circuit design or computer chip design. Okay. And when you do things by using computers to simulate things, it's called virtual prototyping. Okay. In the olden days, when we want to design an antenna or something electromagnetic, you first make that thing, you went to the lab to test it out. If it didn't work, you go and design it again. You went to the lab, tested it out again. It was very laborious. But these days, you can cut and try engineering on the computer. You design a certain thing, it doesn't work. Go back to the computer, go back to the drawing board, and redesign the antenna. Test it again, it doesn't work. You do cut and try engineering until it works. You'll be amazed that nowadays, like the computer chip design that you have in the cell phone, 95% of that is designed with software. You use software design called 5 and then electromagnetic solver. And try to do as much as possible with software. That can cut down the cost of the design rather than having you to rebuild the things over and over again. So there will be lots of cost savings. Okay. So let's try to understand how a half-wave dipole works. This is a half-wave dipole. A half-wave dipole will have a current distribution that looks like the sine wave.
And in order to understand why it looks like a fine wave, you can think of this as a transmission line. And if you have a transmission line, which is half a wavelength long, or quarter wavelength, this is half wavelength, but one side of it is quarter wavelength. You can think of having a transmission line which is quarter wavelength. And the current distribution will look something like this. Okay. So if you drive it with the current source on this side, then the current distribution will look something like this. Okay. So the maximum on the left, then on the right hand side is the cube. So it looks like a quarter of the wavelength. Now if you open up this transmission line, let it flare, and the current distribution will still look something like this. Maximum at the place where you drive the antenna, but going to zero at the end. But even if you open it up, the current distribution is going to look like this. Okay. So we use the transmission line intuition to infer that the summary distribution on this antenna looks like that of the transmission line. Any question on that? A very interesting antenna is called the Yagi-Uda antenna, which is invented around 1926 by two Japanese scientists. Okay. And the amazing thing was that the design was arrived at completely by using physical intuition. No simulation. And we found that if we have a element, a radiator, the ray of light will be put in the front of the radiator and act like a waveguide. Other elements will be slightly longer. So this array of antenna force or direct all the energy to go forward in the forward direction. So if you don't believe it, seeing is believing. So I had my students simulate this antenna many years ago. I hope it works. Oh yes. Yes. You see, I'm kind of dumb on this kind of thing. Okay. So it starts to simulate. You can see that the energy is moving upward. And it has to be studied where the reflected at the bottom. Okay. They are like this. Okay, this is active dipole element, a very simple one. These are the director, the actual waveguide, and this is the reflector. Okay. Nowadays, people have made this antenna in terms of nano antennas. They're very small. They operate in the region of blue light or something, or maybe infrared light. You can make an array of them and so on. Okay. Another antenna that is very useful is called a cavity back slot antenna. So if you have just a dipole alone, it doesn't radiate well. It just doesn't radiate well. It looks like a capacitor, and you have to pump it with energy. However, if you put this dipole inside the cavity resonance that you have shown before, and if you force this dipole to operate near the resonance frequency of the cavity, what will happen to the electromagnetic field inside the cavity? You don't have to understand cavity analysis. You just have to understand circuit analysis. So you have an LC tank circuit. You come an LC tank circuit with a force, the current source or the voltage force, goes to the resonance frequency of the LC tank circuit. What happens to the current on the LC tank circuit? Yes.
LC10 circuit doesn't propagate. So what happens to the current on LC10 circuit? It will grow, right? It will become bigger and bigger and bigger. Okay, you can see this mathematically as well as physically. That if you pump an LC10 circuit at its resonance frequency, you get a growth in energy. And eventually, if you put this dipole inside the cavity, and this dipole operates in the resonance frequency of the cavity, the energy inside the cavity will become bigger and bigger. I have this particular Mason problem. Ask you what happens to the energy of the single cavity. Is it infinite or is it finite? Is it something? The answer is that it should be finite. Because it's not something of the cavity. So the energy in the cavity is energy conservation. But if you would pump the cavity with external energy, the energy will grow bigger and bigger inside the cavity. So this is what happens. The electromagnetic field inside the cavity becomes stronger and stronger. And then if you look at the field at the aperture of the hole, which we call the slot of the container, the electromagnetic field is very strong. And it will start to radiate what? Radiate better and better. And this is how a cavity back slot container works. Okay. You can also make microstrip patch antennas to make them radiate well. These are very popular because they're easy to make. You can make them by you have some copper flat wall. You have some hydrochloric acid. You have some resistive. I think they call resistive. Things that does not get comfortable away with hydrochloric acid. You take the paper back, you open the tank of solution for a couple of hours, and after you come back later, you can see the patches to make copper glass door. So they're extremely easy to make, no cost. But if you look at this antenna, it consists of an upper half straight and a lower half straight. So when you have two straight together, what comes to the mind? The answer is one thing, but what happens to the electrodynamics? What? It looks like waveguide which is true, okay? And this waveguide has open surface and all four sides. So in order for us to think simple, this thing of it is a transmission line is open surface on both sides. That will make a rational. So an open circuit transmission line, both ends make a vacuum. So this will make a vacuum because the current just goes back and forth away. Just goes back and forth between the two ends, making this into vacuum. So to have the vacuum, the only difference is that it's not a perfect vacuum. Energy will be out on the agent. So the Q of this is not high. It's a low Q resonance. That is good. Low Q resonance because we want to continue to radiate. If it's high Q, it's not so good for us. And all that energy is just cut. So if you excite this antenna near its resonance frequency, we'll start to radiate. If you agree. And yesterday is a very good antenna with the radiation. If you operate this antenna close to the other frequency, it doesn't radiate. It radiates forward. And then the bottom part is kind of the continuous engineering strip. You have the inset for the feed. Because you have this inset for the feed, and if you think of current flowing on the patch, in the top patch, the current is just flowing back and forth like that. Okay, this is an open circuit. So this is very much like the transmission line problem. The top one, the current just go back and forth and there'll be waves going back and forth like this. The bottom one, the current goes like this and like this. And the current has a longer path to flow through before it reverses its direction. So the size of the cavity appears to be larger to the current which goes back and forth. In the bottom design compared to the top design. Top design you only see top of the length for the current to go to the floor. But the bottom design will also goes back, forth and back and forth, and making the reference frequency low. What is the advantage of designing an antenna with a lower reference frequency? Yes. Very good. You can make the antenna small. Say if I wanted to be operating at 10 gigahertz, the full wavelength is 3 centimeters. Half wavelength will be 1.5 centimeters. Okay. So if I can make this antenna resonate to the lower frequency, to make it even 1 centimeter and start do that. So you have to gather this concept around. The lower the resonance frequency, the smaller the antenna. So low resonance frequency is very important in cell phone design. You want to stick all this antennas in cell phones do not give you a lot of space. I'll stop here and let you go.